Good evening, everyone, and welcome to today's second evening presentation. My name is Guillermo Aldama-Bustos, and I will be the chair for today's presentation. Today, we have an online meeting only presentation. You will be able to submit your questions at the end of the presentation using the Q&A tool on your window. You can type your questions as the presentation goes along, or you can do it at the end. I'm going to be reading out loud for the various presenters that we have today. Please be aware that this presentation will be recorded and later shared in our YouTube channel, which will be available to the wide public. So therefore, by joining the call today, you consent that any comments or information that you share will be made public. So today, it is my pleasure to introduce three different speakers. We have David Hawthorn from BGS, and we have Iain Tromans and Angeliki Lessi-Cheimariou, both from Jacobs. They will be talking about the installation, operation, and data processing of the borehole seismic array that was installed at the Bradwell B nuclear power plant. David is a seismologist with the British Geological Survey. His current work is strongly focused on the management of the UK permanent national network, as well as smaller temporary networks deployed to achieve more specific targets. His work also involves operating several site-specific seismic stations and nuclear licensed sites and dams, which are integrated within the wider seismic network. He has been working in the field of passive seismology since 2007 for both academic and governmental organizations. Iain Tromans, he has about 22 years of experience in engineering consultancy. He has been heavily involved in seismic hazard assessments for critical infrastructure with emphasis on nuclear facilities. He has been closely involved in all aspects of the delivery of the prolific seismic hazard assessments recently done for Hinkley Point C, Sizewell C, and Bradwell B. He is the head of technology for seismic geotechnics at Jacobs. And our third speaker, Angeliki Lessi-Cheimariou. She's a senior earthquake engineering specialist engineering specialist at Jacobs. She has over 16 years of experience in site response analysis and site characterization. She has led on these aspects of the PSHA studies for the sites that I already mentioned, Hinkley Point C, Sizewell C, and Bradwell B sites. Her experience extends across the broader geotechnical and earthquake engineering fields. So my appreciation for all three presenters to agree to give these presentations. I hope everybody will enjoy the presentation, and then I hand over to Iain, who is going to be the first of our speakers. Iain.
Thank you very much. So today's presentation is split into three parts, and I'm going to kick off with a description of the benefits of on-site earthquake monitoring for nuclear facilities, focusing on the regulatory guidelines from the IAEA and from the ONR. Also looking at how the benefits are to reducing uncertainties in the inputs to PSHA. Then I'll hand over to David, our collaborator on this work at Bradwell B, from the BGS, who's going to cover the technical and logistical aspects of the deployment and operation of the Bradwell B borehole seismometer array, and how he was involved and led the integration with the wider national seismic monitoring network. And finally, I'll hand over to my colleague Angeliki Lessi-Cheimariou, who will present on how we have used weak motion records collected from basically an 18-month period during the operation of the array, and how we use this data for various aspects of the PSHA model specifically focusing on the validation of the site response and better characterization of the uncertainties associated with that. So part one, benefits of on-site earthquake monitoring. I'm going to talk about the IAEA guidance using the acronym SMNS, which is the Seismic Monitoring Network Systems, which is the one that the IAEA are using in their latest draft guidance on this topic. I'm going to then talk about what they refer to as SMNS for site evaluation, because that's what we're focusing in on today's presentations. I'm then going to talk about the Office for Nuclear Regulation recommendations, and finally summarizing the main benefits of the monitoring systems to PSHA's probabilistic seismic hazard analysis. So first of all, what does the IAEA guide us? Does it recommend the use of seismic monitoring systems? I want to kick off with a quote from the specific safety requirements SSR1, site evaluations for nuclear installations. Requirement 28, regarding monitoring of external hazards and site conditions. And I quote, all natural and human-induced external hazards and site conditions that are relevant to the licensing and safe operation of the nuclear installation shall be monitored over the lifetime of the nuclear installation. So there's a very clear instruction there from the IAEA about the importance of monitoring in this context. Then I've got another quote here from SSG 9, the Rev 1, which was from 2022. This is the IAEA guidance on seismic hazards in site evaluations for nuclear installations. And again, I quote, the seismic monitoring network system should be installed for new sites from the very beginning of the site evaluation stage. For existing sites for which such systems were not originally deployed, the seismic monitoring network system should be installed from the beginning of the seismic safety re-evaluation program. These systems should be operating during the whole lifetime of the nuclear installation. There are two main objectives from seismic monitoring systems, and they're quite different. The first one, and we find a lot of guidance in the IAEA documentation about this, it's for warning operating personnel during an earthquake, and potentially also for auto shutdown of nuclear power plants. The second objective is collecting detailed information on the characteristics of ground motions at and around the site to support site evaluation. And the IAEA make this distinction between these two different purposes with the subscript SE, which is the site evaluation aspects. So on the right-hand side, here's a figure of a nuclear power plant. We've got points A and B, which are some distance from the plant, which are recording free field motions. These are connected to objective number 2, relating to site evaluation. And the instrument that's indicated on the base map, an in-structure instrument, this is related to objective number 1, which is measuring the vibrations within the plant itself, not a free field motion. And this is for warning and potentially for safe shutdown of a reactor in the event of a large earthquake. So all three presentations are focusing on the free field instruments that help with the site evaluation aspect. So the different types of system have different are used in different stages of the work and are used and have different purposes. And this is another extract from this latest draft document It's a tech doc. Tech docs are, there's many very useful tech docs produced by the IAEA on specific technical aspects. And this is going to be released later this year. And I've managed to get hold of a draft version, which I'm just sharing some extracts today. It's the establishment and use of seismic monitoring network systems for nuclear installation sites. So looking at this table, the SE, the site evaluation systems, are used primarily in the site selection and the site characterization stages, but they're also used throughout the lifetime of the nuclear installation. This is used for monitoring seismicity to collect data for building the site-specific seismological database. It's used for supporting the development of seismic source and ground motion characterization models in seismic hazard assessment. And it's also used for supporting seismic site response analysis. Those network systems related to operation, looking at the second row down, these are purely used during the operational stage, and it's primarily for recording earthquakes for decision making during and after an earthquake. So looking at a few more details about the site evaluation systems on the first row. So these contribute to the project-specific earthquake catalog to improve statistical stability of the magnitude-frequency relationships. Helps in the selection of ground motion models, the data that comes from these monitoring systems, and also for estimation of non-ergodic terms for use in the seismic hazard analysis. Also provides an estimate of high frequency damping, the kappa, that you may have heard reference to, and of site amplification. And it can also provide information on path effects, empirical Green's functions, and helps evaluate ground motion prediction equations and site response. Whilst those related to the operation, the warning and alarm systems, are triggered by threshold values of ground motion, and they can actually trigger, especially in high seismicity areas, automatic lockdown of the power plant. These systems also inform operational decisions related to shutdown and help determine the plant status and whether a plant is able to restart. These warning and alarm systems, there's plenty of information in the IAEA guidance. I'm not going to talk about them anymore, but I just want to refer you to these documents on the screen. One of the tech docs, a safety report, and one of the specific safety guides, SSG 67, which presents some very useful information about this if this is something you're interested in. This is an example. This is actually a map on the left-hand side of the world's largest nuclear power plant in Japan, run by TEPCO, the Kashiwazaki Kariwa nuclear power plant, which has experienced some rather large earthquakes over its operating life. This map on the left shows 5 different locations where there are 3 field instruments. There are 4 borehole arrays, and 2 additional surface instruments installed, all for the purposes of site evaluation. Each of the reactors that you see also has systems for alarm and shutdown, and there are 7 different plants here. On the right hand side of this figure, we see shear wave velocity profiles for 2 of the borehole arrays, showing that there's data, shear wave velocity data going from surface all the way down to up to 300 meters depth. This is quite typical of many of the nuclear power plants in Japan, which have, in many cases, several borehole arrays installed for obtaining data for site evaluation purposes. So it's SSG9, which I've already referred to, which provides guidance on the seismic hazard assessment, covering both vibratory ground motion hazard and capable faulting hazard. And the benefits of seismic monitoring cover several areas related to seismic hazard assessment. And just really pointing out and highlighting some of these aspects. Event identification and source characterization in terms of identifying the location and the magnitude of earthquakes is a real benefit from these systems, especially when installed as a network or integrated into an existing network. And this is the aspect that David is going to be talking about and focusing in on in part 2 of today's presentations. There's also the benefit of identification of active faulting where this is suspected, particularly in areas of high seismicity. This requires a dense local network, typically. And the third point is, the third benefit is the ground motion data, which can help with the development of site-specific non-ergodic ground motion models, can provide information on site attenuation and site effects, among other things. And I refer you to the section 3 of the SSG9 to give more details on that. Moving now to the recommendations from the Office for Nuclear Regulation, which is specifically relevant in the UK context. The general recommendations on the monitoring can be summarized in this quote from the SAPs. The SAPs are the Safety Assessment Principles, and for EHA2, for external hazards, it emphasizes in paragraph 237 that site-specific data should be collected and used to support and/or validate calculations of external hazard event severities and frequencies. So, of course, the ideal is to have site-specific data rather than relying on generic data. Referring to the Technical Assessment Guide 13, which is specifically focusing on external hazards assessment, within Annex 1 the reference paper, there's a few specific recommendations regarding monitoring. Firstly, that installation of seismic recording instruments, especially borehole installed instruments, is of great benefit. The emphasis is that the maximum benefit from these systems is from the earliest possible installation during the life of the facility. The data can be useful for estimation of the high frequency damping parameter kappa, again, as we've heard from the IAEA guidance as well. It's also useful for verification of linear amplification factors for site response analysis. The other thing that's mentioned here is that it's useful for calculation of the horizontal to vertical spectral ratios of weak motion, which is of great use for estimating the fundamental frequency of a site. So what are the specific benefits of these seismic monitoring systems for probabilistic seismic hazard analysis? Now, in modern practice of PSHA, there's a great emphasis on understanding and characterizing of uncertainties associated with the input parameters and the models. You may have heard mention of the SHAC process, which goes back to the mid-90s. The SHAC process is a way of incorporating uncertainties and different understandings of models and data sets within a seismic hazard analysis. SHAC stands for the Senior Seismic Hazard Analysis Committee, and arose from some work in the US and has since undergone a couple of updates since 1997, the original SHAC study, and there's been some updated guidelines up to 2018. And SHAC process has been adopted and implemented in many countries, including the UK. Now, the diagram on the right-hand side is a flowchart illustrating PSHA, specifically the two-step process, where the first step is the calculation of the bedrock hazard, anything below the bedrock horizon on the right-hand side. And the second step is the analysis of the site response, which is then combined with the bedrock hazard to get the surface motions. Within this process of PSHA, there are other ways of doing it, like the one-step approach. But within this process, there are specific elements which benefit from site-specific ground motion records. And I've highlighted these in red on the right-hand side. So looking at the bedrock hazard, the kappa naught is something which is used in the VS kappa adjustment factors, where we take ground motion prediction equations from data-rich host regions, and we apply adjustment factors which are site-specific to get ground motion prediction equations which are more appropriate for the target conditions, for the target site. The VS comes from understanding, comes from measurements of the deep velocity profile, which requires data from ground investigation. But the kappa naught is something which we can obtain from ground motion records, even weak motion records. So this gets used in the modification of the ground motion characterization, the ground motion model, to make it specific to our site. And then looking at the site response element above from the bedrock up to the ground surface, the main inputs to this is the site property model, which combines shear wave velocity data primarily. It's one of the main inputs. We've got G over G max. This is shear modulus curves against strain, and damping curves D against strain. This is the data that's needed from ground investigation. This is input into a site response analysis to get amplification factors at the ground surface. However, if we've got ground motions from a borehole seismometer, this allows us to compute amplification factors directly from empirical data by dividing the site response between two different pairs instruments of a pair of instruments. This gives us a way of validating the 1D site response analysis against actual data from the field. Of course, one of the key aspects here, prerequisite, is that we've got a reliable site property model from a carefully designed and implemented ground investigation. And I'll refer you to the Bradwell B example that Angeliki will give more details of later. So at Bradwell B, we helped to design and install a Guillermo radian borehole seismometer. And this was during the site evaluation phase of the project. And this fed into the PSHA that we were doing at the time. The figure on the right-hand side shows we're in the London clay. There were three instruments, top to bottom there. We've got one in the London clay, um, um, the top of the London Clay, the second was towards the base of the London Clay, and the third one, crucially, was in the chalk, the top of the chalk. Then this allowed us to have comparisons between the bedrock motion and various different elevations within the soil column to understand what the site response was. And we only actually had access to 18 months of weak motion records during the period that we were doing the seismic hazard study. But this, nevertheless, even with the low seismicity of the UK, this allowed us to come up with an estimate of kappa through our collaborator, Dr. Olga Katenidou of the National Observatory of Athens. And she was able to compute the uncertainty bands around the kappa value at the chalk bedrock, which then fed into our ground motion prediction equation and the host to target adjustment of that model for the Bradwell project. We also were able to obtain detailed a number of sets of records which allowed us to understand the site response and the site effects. So these data provided immediate benefits for the constraining these input parameters for the PSHA, but I also want to highlight the long-term benefits of having such an array installed at a nuclear power station site or a proposed nuclear power station site. As the database grows with time, there is an increased scope for better constraining the uncertainties and associated with the input parameters, and therefore ultimately improving the site-specific estimate of hazard. So in the UK context, where we have periodic safety reviews every 10 years or so, this potentially allows for some beneficial updates to PSHAs and a reassessment of margins associated with the design of the facilities, which is of great benefit to the facility operator. So this concludes my presentation. I'm going to hand over to David, and just closing out with a nice aerial view of the Bradwell B site. Bradwell A there is seen in the foreground, which is now under decommissioning. Bradwell B site was being planned for use for a new couple of new nuclear reactors, which is currently on hold. But I'm going to hand over now to David. I'll just pause briefly whilst I'm swapping over the presentations.
Thanks very much for that, Ian. Can you hear me okay?
I can hear you loud and clear. Thank you.
Perfect.
And I'm just...
And I'm not seeing any slides yet.
Yeah. Sharing now.
There we go. Thank you very much for that, Ian. So as Ian mentioned, I'm going to talk about more of the kind of logistical aspects of how we kind of installed the station, how we designed all the kind of equipment around the station, and how we incorporated it with the wider seismic network. And to do that, if I can get the next slide, please, I'm going to talk more specifically about, I think, firstly, especially if you come from a background of just working in terms of seismic hazard, I'm going to talk about why it could be advantageous, even when you've got a sense to do something very specific, that there are wider benefits to incorporating it in a wider seismic network. I'm going to talk about the specific equipment that we chose, the Gurat radiant system that Ian talked about. And I'm going to talk about how we designed the station, so how we powered it, how we got the data out of it, how we housed the equipment on site. I'm going to cover the deployment of the station physically in terms of how we got the stuff down the boreholes. And I'm going to talk a bit about how it's integrated with the network in terms of the data management. And I want to talk a bit about, in kind of practical details, what we were doing on a day-by-day basis in terms of managing that really kind of accurate machinery, that sensory apparatus. And finally, I just want to finish off about how we how we would expect this to have been used in the future. Sadly, Bradwell's in a bit of a hiatus at the moment while they work out what they're doing with it, but we can use examples from other power stations of how this could have been used over the lifespan of the station as it went in. So if I can get the next slide, please. So firstly, I wanted to talk a bit about why we think there's a really kind of strong case for pretty much any site-specific monitoring system to be part of the wider network. So on the left here, you can see a map of the UK with all the seismic monitoring stations that are deployed in it, including Bradwell down in the on the east coast. And the first and really obvious reason for doing it is it reduces the detection threshold. So essentially, the more monitoring stations you have in a given area, the smaller the magnitude of earthquake that you can detect with them, and the more accurately you can do that. So next slide, please. So the map on the left is we created back in 2018 at the start of this project, and it shows the modelled detection threshold across the East Anglia area. So those ISO lines show the smallest possible detectable earthquake. The red triangles were the existing BGS stations at the time, and the yellow circle is where Bradwell is. So you can see we modelled that the smallest earthquake you could detect at Bradwell itself would have been about a magnitude 2.4 at the time. Next slide, please. And if we if by deploying an additional station at Bradwell, you can see that drops it to magnitude 2, and overall that whole area you can basically detect almost half a magnitude smaller earthquake as a result of doing it. And you can also do that more accurately, and particularly for small near earthquakes, that enables you to get the depth of that earthquake really well. There are some other really good reasons for doing it. The first is that if there's an existing seismic monitoring network in the country, that network will already have a whole set of data management routines for getting that data into their servers, for processing it, for archiving it, for automatically generating alarms and identifying earthquakes. And also any network, and we're no exception to that, will have a whole suite of programs that are designed just to look for possible errors in the station. So for instance, on our own network, we're constantly looking at the supply voltage, particularly for solar panelled sites, which you're seeing plotted on the top left there for one station. We look at the amount of data arriving on our database. We look at the amount of that data that arrived in real time. That's that middle graph for a station. And there you can see we're starting to see an error associated with the amount of real-time data that we're getting from a station. We look at things like the mass positions and how they change within the sensor themselves. We look for specific error messages in the log files. And whenever the system finds this, it generates an alarm email that goes to an engineer, and it means that they can identify or rule out a potential problem. And none of this is rocket science. Iain's got a very competent team. I've got no doubt he could recreate all of these systems from scratch, but it would take a lot of time and effort. And if there's already a body that can do that for you, it potentially makes life much easier. The other reason for doing this is validating your data. Oddly, if you have just one seismic monitoring station in your portfolio, it can be really quite hard to know if it has a fault. If you start to suspect that, for instance, the timing is not quite right, or that the sensors are going out of calibration and slightly over or under reading a ground motion figure, if you have nothing to compare it to, you can really be scratching your head over it. Whereas if you're processing the data from multiple stations at the same time, you can compare them with each other, and it gives you confidence that your equipment is working. And that's particularly over the lifespan of a power station. When your equipment is shiny and new and it's less than 6 months old, the chances of there being a problem are pretty rare. 5, 10, 20 years into the life of a station, if you're constantly using it as part of a wider seismic network, you can be much more confident that everything's working correctly. And finally, it kind of, as Iain was mentioning, it makes it much easier to demonstrate to any kind of regulatory body that you're being really proactive about your approach to seismic hazard, because you're literally taking part in monitoring the entire sort of regional area around your site. Next slide, please. So with that, I'm going to talk a bit about the equipment that we went for. So we're using borehole sensors here, and borehole sensors are nothing particularly new in seismology, but there've been really radical changes into how easy they are to use and the cost of them. And we went for a system produced by a company called Guillermo, based down in Aldermaston, and specifically their radian borehole sensor. So on the image in the left here, that's what that man is holding in his right hand. That's a radian sensor. And specifically, they work by what are called hole locks. So if you see just above his hand, there's a kind of knobbly bit on the sensor. There's another knobbly bit at the bottom of it. And these are mechanical arms that can be remotely activated. So you can lower that sensor to any point within the borehole, activate the arms, and it clamps against the walls of the borehole. And that means it's held firmly in place at a specific height within that borehole, and it's well coupled with the walls of the borehole. So any kind of ground motion will be well fed into it. And one of the ways that borehole sensors have really come on, so it used to be you pretty much had to have an almost perfectly vertical borehole. The radian sensor can be deployed at any angle at all, including completely horizontal. And in this case, that was fantastic because it meant that we could just use a pre-existing borehole. Didn't have to drill a new borehole for it, which probably would have cost more than the cost of all the equipment we would have put in the borehole. So that's a really strong point for it. The radian can go down to any depth up to 2,000 meters. You can see it's a very thin sensor. It's 55 mil in diameter, and those looking arms enable it to fit within any borehole within a 60 to 100 mil inside diameter. I think the company also make a model that has larger locking arms, so you can put it into an even larger borehole. And again, the other nice thing about this specific model of sensor is, if I can get the next slide, please, is you can daisy chain them together. So each sensor has a connector at the top and the bottom. So you have a cable that runs to the top of the sensor and then another cable that runs out of the bottom sensor to the next sensor. And again, people have been putting multiple sensors down boreholes for quite a long time. But until this system came along, that meant that each sensor had to have its own entirely separate cable and its entirely separate data logger. So, the cable at the sensor at the top of the borehole would have another 2 cables going past it. And that's a real pain to do in terms of installation, recovery, management of multiple data loggers. And these sensors are accurate for frequencies of ground motion between 120 seconds and 200 hertz. Next slide, please. So how did we put all of this together in the field? So we went for a solar and 4G option. So we had 900 watts of solar panels and 460 amp hours of lead acid batteries. And that was because of the overall power consumption of the site was 15 watts, about 10 watts for the sensors and the data logger, and about 5 watts for the 3G router that we had on site. Worth noting that that's because this is a comparatively shallow borehole at 100 meters. As soon as you go over 100 meters, the power consumption starts to go right up because of you have a much higher power current draw from getting that signal down those longer cables. And in turn, that might have meant it would have been less practical to have solar panels. Now, each of those 3 sensors has 3 components in it. So an up-down component, a north-south component, and an east-west component. And each one was recording at 250 samples a second. So that's about 300 gigabytes of annual data transmission. That's quite a lot of data. Normally, we'd prefer to use something like a satellite system or an ADSL line for that. But those would have had much higher power consumptions, which is why we went for a 4G option, because we could run it off solar. And those sensors were deployed at 15 meters, 46 meters, and 96.5 meters below ground level. And as I mentioned, that was in a pre-existing borehole that didn't have to be drilled. So just looking at those images on the left there, top image shows Bradwell power station right at the back, the solar panels we used, and behind one of those solar panels is that big green box that sits on top of the borehole, as you can see in the middle image. And on the lower image, that's what you would get if you open that green box up. So you've got that yellow thing is the data logger, batteries on the right with a 4G router sitting on top of those, solar regulators. You can just see those blue things on the left. And that blue cable on the top of the data logger is going down into the borehole, which you can't quite see because the data logger is on top of it. Next slide, please. So station deployment was done by the manufacturer. So they send a 2-person team. It's not a particularly complicated process to do, but it needs a degree of specialist equipment, the winches, the tripods and so on. So unless you're doing an awful lot of these in a year, it's probably not worth you getting your own equipment to do that. It takes 2 days to do a deployment. So generally the deployment is complete by the end of the first day. But then the problem is, because these are borehole sensors, you need to know how they're orientated in terms of north. And to do that, they leave a temporary sensor just at the surface overnight. And in the morning, you can use the ambient noise from overnight, and you compare the surface sensor with the borehole ones, and you can work out the orientation of the borehole sensors. And finally, what they're always looking for when they do this deployment is that the manufacturers want a kind of a confirmation that you're happy with the data quality. And in this case, that was done by me on behalf of the BGS. So we look at the overnight data quality with the manufacturer, and we confirmed that we were happy with the quality of data from all 3 sensors. Next slide, please. So I don't want to go into too much detail, but I wanted to talk a bit about how we got the data back to us. So all of our sites across the UK come back via a mixture of 3G or satellite or ADSL. The first thing to note is, if you work in an organization that has any kind of cyber essential kind of security criteria, the thing that is probably going to take you longer than anything else is persuading your corporate IT to open up the firewall in the right way. Luckily, because we've been doing this for literally decades now, we had a firewall that was pre-set up for all the different types of seismic equipment that we have, including the stuff that went in at Bradwell. So that was already pre-done. Then we used the manufacturer's specific software to carry out data streaming between each remote site and our primary data server. So the Bradwell data would come into our primary data server. It goes into a short-term archive. And from that short-term archive, we've got 2 data flows. One goes to our automatic earthquake detection. So that's the earth event detection system. That uses an SDA, LTA comparative system. And whenever it thinks there's an earthquake, it flashes that up to one of our analysts. They confirm or deny that, and they create an alert. They classify it in terms of the location and the magnitude. And the other data processing stream is that short-term archive. About every hour, we take a copy of the latest data in that, and that goes to long-term archive. It's formatted in terms of all the guidance for international standards of passive seismic data formats. And then it goes into our kind of long-term double redundant backup system. Now, for most of the network data, that then becomes publicly viewable and accessible. But because we were running the station on behalf of somebody else, it still gets all the kind of backup, but it's not publicly viewable or accessible or downloadable. And all through this stage, we're doing that kind of state of health analysis where we actively try and look for any kind of suggestion of a problem with the remote station. So log records, voltage records, mass fluctuations, latency figures, all of that kind of thing. And the next slide, please. And the final part of this is we have an entirely redundant system. So everything I was just talking about happens in Edinburgh, and we have a clone copy of that occurring in our Nottingham office, so that if either one drops out, we have a redundant system. Next slide, please. So we were under contract to manage this site between 2018 and 2021. And during that period, we produced a monthly report that went to the operators or the developers of the site. It went to Iain as well. And that listed any faults that we might have investigated in that period. It listed the data completeness, and it listed any earthquakes that we in the BGS picked in using the data from this station and other stations. I went and got the analyst to run the numbers on that. And during that period, we picked 178 distant earthquakes and 361 local or regional earthquakes. The reason we're interested in distant earthquakes is partly because of, we're a government organisation and bits of government want to know that. But from my point of view, they're really good for checking that your system is working. A big distant earthquake we can detect on all stations across the whole of the UK. And again, it's that issue of saying all of our stations are working, or I don't like the way that station looks. It should have been the same for that teleseismic event. Although we have automated systems that look for any small data gaps that might have been caused by, for instance, a dropout in the 4G quality, sometimes that doesn't work for whatever reasons, and we get a notification of that. So about 2.5 times a year, we would identify one of these gaps and we would manually backfill it. So we had a complete archive of all data. And those state of health checks meant that we made 54 separate remote checks in response to some perceived problem it might have had. So about 17 times a year. Now, some of those were false positives, and the ones that weren't, we were able to resolve remotely, because during this time frame, we didn't have to visit the site at all. Next slide, please. Now, sadly, the kind of development plans for Bradwell went into kind of a bit of a hibernation in 2021, but the developers were kind enough to say that, you know, we could continue to use the data from the station, even though they weren't actively developing it. Now, we couldn't afford to do that within the sort of the format that it was in, particularly in terms of data volume. So what we did was we altered the sample rate to 100 samples a second, and we only streamed the data from the lowest sensor. And we can still use that to detect and locate earthquakes around the area. But one of the really nice things about this manufacturer's specific offering with the Radian is you can stream one sample rate of data, but you can record internally another. So all three sensors are still recording at 250 samples a second, and we can do a manual download. And I think since 2021, there's been at least once where there's been a really juicy local earthquake, and we've gone on and downloaded that 250 sample a second and archived it in case it's needed in the future. And again, we broke the kind of the back of the no site visits. Since 2021, we've had to visit the site 5 times. So once that was associated with the scheduled shutdown of the 3G network across the UK, and we had to upgrade the router to 4G. We had a faulty battery that needed replacing, and the data logger developed a fault and had to go back to the manufacturers for an under warranty repair. Next slide, please. So finally, I just wanted to talk a bit about, you know, sadly, we're not looking at certainly an imminent development of Bradwell, but if that was going to happen, and maybe it still will, what might we do with the station in the future? Well, it's worth noting that the two really expensive things about this station were the creation of the borehole and the purchasing of the hardware. All of that's out the way now. And to this day, we've got an entirely operational station. Now, that means that we continue to locate events and we continue to use those to more accurately develop a catalogue of earthquakes in the southeast of England. It also means that we're continuing to keep a record of those events, including the specific ground motion at Bradwell itself. So as Iain was talking about, it gives the potential for future reviews of the original safety case. And it continues to lower the detection threshold across the area, which in turn gives you more data to work with in terms of any safety case. If the site was developed as a power station, it means that, you know, like a number of other power stations around the UK that have seismic monitoring, if there is an earthquake, you know immediately what the specific ground motion is that's affected you. You're not dependent on a predictive equation to tell you that. And again, there's a number of other stations around the UK, power stations that have a real-time alarm. So they're not reliant on an analyst. They use the data from the sensors that they have on site to tell them not only that there's been an earthquake, but exactly how much it's accelerated either the site or different parts of the site. Now, you would have to do a small amount of additional work to the station to turn it into one of those autonomous earthquake alarm systems. But the cost would be really minimal. I mean, probably less than 5% of what you've already spent in terms of deploying the borehole stations, because you really just need that far field additional station at the surface to root out false positives. So potentially you've got a real asset for the entire lifespan of any future power station. And with that, that really covers all the kind of logistical items, and I can hand on to Angeliki for what you've probably all been waiting for, which is what was actually done with all the data from the station.
Thank you very much. I hope you can hear me okay. So this is the last part of the presentation, how we use the weak motion data for Bradwell B probabilistic seismic assessment. So it all started from the collaboration of the China Nuclear Power Group and Électricité de France. They joined forces to develop a new generation power plant at Bradwell B, which in its capacity could provide potentially up to 5% of UK energy. So it's a big project. Jacobs was assigned the probabilistic seismic hazard assessment for the site, as well as the capable faulting study. And as part of that, we scheduled and supervised a major ground investigation, which also included the installation of the borehole array. So this was the firstly installed and operational borehole array in the UK, which, as David and Iain mentioned, comprised 3 broadband seismometers, 3 sensors, and it was programmed to have a flat acceleration response of the 0.083 to 200 hertz. So this allowed it to capture surface waves from distance and large earthquakes, as well as low frequency side effects, which would have been otherwise been missed, but also to capture high frequency response, which we needed for the kappa definition. So the comprehensive ground investigation comprised numerous intrusive and non-intrusive techniques, as well as a very detailed laboratory testing campaign comprising advanced testing for the definition of the nonlinear properties which we needed for the site response. So the intrusive measurements included PNS and suspension logging. So we had several profiles for that across the site. And we had 18 seismicity profiles and 2 clusters comprising 3 cross-hole measurements, as well as 5 surface to downhole testing. The ground investigation also had numerous non-intrusive surface wave techniques, which are very interesting to see how they covered the site, and they included a seismic reflection, as well as the conventional multi-channel analysis for surface wave MSW using the conventional hammer source. We also had the luxury of using the closely spaced geophones with explosives used in the reflection, reinterpreting this data using surface waves to extend the resolution depth of the conventional MSW and reaching the depth of the chalk. So that provided a more complete and continuous profile through this interpretation of the data. We had a 2-dimensional microtremor array, including different aperture size circles, which gave us the possibility of obtaining a dispersion curve, which covered an extensive range of frequencies and wavelengths and consequently depths. And we have a detailed campaign comprising single station microtremor based on ambient noise, and obviously the installation of the borehole seismic array. So now the importance of having such a comprehensive ground investigation, but also these different techniques in order to characterize the site, gave us the obviously the ability in answering the demands of site-specific data for the PSHA, namely the dynamic soil properties, but also allows to characterize in detail the ground model, which Iain briefly mentioned, and I will refocus. So following best practice, we had the ability of comparing inter and intra method variability on specific parameters, and having a robust definition of the site properties. So you can see on the left-hand side, these are the usual suspects of the London Basin, London Clay Formation, Harwich Formation, Lambeth Group, and Thanet Formation. These were the softer sites, the softer sediments under our site, before we met the chalk, which was the reference velocity horizon for our PSHA. What is interesting to note from these 3 different slides, is firstly on the left-hand plot, the fact that the geological units are mainly subhorizontal. In the middle part, we see a remarkable agreement of the P&S measurements across the site, with some increase in stiffness, which was explained geologically by the presence of claystones. And all of that corroborated a one-dimensional site. So let's see how the data describe further the one-dimensional nature of Bradwell. So refocusing firstly on the downhole array itself, this was installed at a critical point along the timeline of the project, and this is very important for the installation of such instruments in order to have sufficient time to record and be able at the same time to use the data set within the time frame of the analysis. So it's of essence to install it at the right time. So we had 18 months of recordings with 64 events in total from our 3 instruments. So the sensors were strategically installed at the top and the base of the London clay, which was coincident with the target level for a site response analysis, that being the shallower sensor, but also the base of that unit, because this was the critical unit for the site response analysis. The deeper sensor served as well for the calibration of the velocity profile, but more importantly for the definition of the kappa, which was a critical parameter for the ground model as part of the PSHA. So I'm referring you also to one of the conferences that was published by Talet-Willett et al. Regarding the analysis of some of the recordings from the downhole array for specifically in terms of the aspect of the kappa VN8 and aspects of the ground model. Next slide, please. So through the period of the 18 months, we have this database of acceptable records. And what we mean by that are records that met certain criteria in terms of noise, so signal to noise ratio. So on the left-hand plot, we see with the red circles, the earthquakes that occurred during the recording period in and around the Bradwell following the installation of the downhole array. The green circles specifically are the event which made the CAD and have been successfully identified as useful for the definition of the kappa measurements. On the right-hand plot, you see the green circles are now translated into magnitude and distance events. So these were again pre-selected. So basically, when we reviewed the data, one of the aspects that we took very seriously was the signal to noise ratio. And this allows to have a characterization system regarding the records and whether they could be used and their quality in terms of the SNR. We have accepted a lower SNR greater or equal to 1 due to the paucity of the events and the seismicity of the region. So next slide, please. So this is an example of the magnitude 3.1 Newdigate event. This was one of the strongest and clear records for our site, and it happened around 100 kilometers from Bradwell. And what is interesting to observe, and the main point to get from this slide, is the importance on having an array as opposed to a single sensor. So on the left-hand side, you can see the recording from the deepest sensor. And the SNR, focusing on the top SNR calculated, is in the order of 400. So the shallower sensor, which is the second set of plots on the right, actually has an SNR which drops significantly to 150, highlighting how much noisier the shallower sensor was in comparison to the deeper one, and highlighting in that sense the importance of having more than one sensor for your array. And for the purposes of obtaining good quality records. Next slide, please. So what we got from the recordings was this kind of record. So the top record was one good record, like the Newdigate event, which was not all noise, but the majority of the records looked like the bottom blue curve. We didn't have, due to the seismicity of the region, a lot of big, strong events. So it was weak motions of mainly the nature of what you see from the blue bottom graph. Next slide, please. So what this meant for the definition of the kappa was that we needed to employ complex analysis in order to be able to extract the information and be able to define the kappa. So kappa being defined as the high frequency attenuation. So what you see on the left bottom plot is the Fourier amplitude spectra and the slope, which was defined in order to establish the kappa for a good record, which wasn't, it wasn't drowning on noise. Whilst the right-hand plot shows the record, which was closer to the blue graph that I was showing before, that needed a lot more work. So what Tenido et al. And Piculis and all the authors that you see on the conference paper on the top of the slide did was to employ complex algorithms which were able to filter this kind of noise and extract the useful information from the records, maximizing the database from the data set that was available. This actually gave us the ability of defining the kappa and its associated uncertainty for Bradwell B, making use of all the records despite their nature through these advanced techniques. So I will refer you more into this conference paper about how this was done and what kind of filtering and algorithms are applied in order to be able to extract that. Next slide, please. So as Iain mentioned, the downhole array was not only allowing us to define the kappa, but also was rather useful in the definition and the assurance offered on the velocity model, which was employed in the site response analysis model. So these two plots we have already shown, Iain and I, and they show the geological succession as well as the PNS measurements across the site. So what we were able to do is to calculate through our acceptable and of good quality records the transfer functions, which you can see on the top right plot. So the transfer functions of those records was calculated, and the average of those was also established, which is the dotted curve. And then what we were able to do was to take the velocities which we established through our invasive or non-invasive techniques and our comprehensive ground investigation, input it into site response analysis, and through numerical simulations managed to tune the Eigin frequencies, the predominant Eigin frequencies that you get from the one-dimensional site response analysis against the mean transfer function and the analogous Eigin frequencies from the vertical array from the weak motions. So that gave us an assurance on the quality of our predicted velocity and measured velocity profile for the shallow case down to the chalk. If you continue on the next slide, please. However, the benefits of the vertical array were not limited to the shallow profile. So what it also highlighted was a low frequency peak, which could not necessarily be explained by the fast and shallow impedance contrast you could see from the velocities in the previous slide at the top of the chalk. So the 0.7 hertz that you see on the HVSRs from weak motions from the vertical array suggested a low frequency peak, which we could only explain by a deeper feature. And quite rightfully, this deeper feature manifested into a strong reflector in our reflection survey at around 300 meters depth, which was coincident with the interface of the Silurian and the Devonian rocks. So this frequency, the low frequency peak, it could only be emulated if we introduce a deeper profile with a feature at a specific depth. So next slide, please. So the other interesting information that came through the HVSRs, aside from the low frequency peak, was this. First of all, this low frequency peak was not evident only on one of the sensors, but consistently appearing in all of the sensors, as you can see from the three plots with the HVSRs from sensors 00 to 02, so from the shallowest to the deepest one. So the gray lines you see on these curves represent the HVSRs from individual weak motion records as calculated. The red solid curve is the mean HVSR for these, and the dust red curves denote the plus minus 1 standard deviation around the mean from the HVSRs. The first interesting observation is, as I said, that we consistently observe the low frequency peak in the HVSRs from the vertical array. And the second interesting observation is that this peak is also coincident with the peak that we observed in the HVSRs from the single station from ambient noise. So the blue curve you see there was from a completely different campaign, and it also matched very nicely the low frequency peak that we saw from the vertical array recordings. The other observation, which are also in tune with what we were expecting from the subhorizontal layers and the consistency of the measurements, was some features that are coincident with one-dimensional site response, namely very clear, very narrow, and very strong peaks, and clear distinction of predominant eigenfrequencies. So all of that was clearly evident from the HVSRs, giving us another assurance of the response that should be expected from the site. Next slide, please. So combining all that information, we decided to extend the shallow profile to and combine it with a deeper profile in order to emulate the low frequency peak at 0.7 Hertz. Information from regional reflection surveys and regional deep BGS borehole suggested that near the Silurian-Devonian interface, we should expect a zero-wave reversal from a geological unit called the gold. And we introduced that reversal and the impedance contrast at that specific interface, aligning all information from the seismic reflection survey, from the vertical array, and from our expectations from regional knowledge. And what you see on the final right-hand plot is the transfer function of that final model plotted against the H over V from the single station based on ambient noise measurements. And that 0.7 frequency peak was emulated very nicely by that final model when we collected all the information from the different sources and techniques. Next slide, please. So what we gained from the downhole array and what the sequence was. So Jacobs designed and supervised a comprehensive ground investigation, which allow us to conduct a rigorous inter and intra-method comparison of the data sets. This multifunctional approach provided the redundancy we needed to define the highly robust dynamic parameters, reducing in that sense the uncertainty in the site's seismic characterization. The data from the downhole array served as a high fidelity ground truth to validate and enhance the field-based measurements. And beyond the near surface, the array provided essential data on the deep impedance contrast, which corroborated the results from the seismic reflection survey. So the process records from the array enabled us to define at the same time as calibrating the velocity profile for the site response, the site-specific kappa values, which was a critical input in the host to target adjustments for the ground motion model as part of the PSHA. So the overall conclusion is that the database of weak motion for sure will continue to grow as long as the array remains operational, and that is a given. And it will provide the prospect for further improvements in the estimation of the site parameters for future updates of the PSHA itself. Thank you very much.
Thank you very much to all the presenters. Really interesting presentation. We have a couple of questions already in the chat, so I remind all the attendees that you can submit your questions using the Q&A tool that should be on your screen. If we move on with the first question from Colin Strain, he's asking, and I think this is for David, what information sources were used to design the station? Example, 4G versus 3G, power provision, and so on. Which other characteristics?
Yeah, so we have a lot of stations. Well, we have a lot of stations across the UK, and they use a mixture of 3G, 4G, satellite, and ADSL. So we're already quite familiar with that, and we were very confident of. We had a default model of what was originally a 3G router and was upgraded through the. So we were very confident both with the manufacturer's specification in terms of its power consumption and its actual power consumption. This was the first of this type of sensor, as far as we're aware, to be deployed in the UK. So we had to go very heavily in terms of the manufacturer's advice in terms of what power consumption it would have. But taken together, that gives you the overall power draw of the system. We used a specific piece of software called NSOL-X for which it designs solar battery systems. So a lot of people make the mistake of thinking, well, it's basically just the latitude you're deployed at. Whereas if you want to be sure, you need to use software that takes into account not just the latitude, but temperature data, because that will affect what capacity your batteries have, and also meteorological data for the actual area that you're in, because of there can be huge differences between, say, the east of the country and the west of the country in terms of how much sunlight you'll actually get falling onto it. And I think that probably would answer the question, Colin, unless I've missed something that you're after.
Please, Colin, feel free to elaborate on your question if you have any more questions. In the meantime, I think we move on to one more question from Barnali Ghosh. She's asking, saying, thank you for the presentation. Who owns this data now, and is this publicly available?
That's probably for me as well. It's owned by China General Nuclear, and it's not publicly available. A few people have asked if they could have a specific piece of data, and they've been kind enough to agree to that. But it's certainly not just publicly, openly viewable and accessible.
Thank you. One more question from Shuabin Zhu. Thanks for the excellent presentations. I have a question regarding the site model. It is understood that the original VS model was calibrated to reproduce the observed linear side response. I was wondering what parameters were adjusted, VS or attenuation? To what extent can the original VS model reproduce the observed linear side response? I think that is for Angeliki.
Yep. So basically, due to the fact that we had such a comprehensive ground investigation and advanced laboratory testing campaign, we had D-mean, so small CS strain dumping, which came directly from the resonant column tests. So this was already well constrained. So the primary parameter that was adjusting through the calibration was the velocities. And that also was very highly linked with understanding of the geology, so the depth of the different geological horizons. So the primary calibration was carried out on the zero velocities and the tuning of the predominant frequencies. So the linear side response that was identified from the H over V based on ambient noise, but also on the transfer function, was very well replicated through all of that.
Thank you. We don't have more questions at the moment in the chat, but I have a question from myself. And probably this will be for Iain. Regarding the cost benefit of these type of installations, particularly for critical infrastructure, what kind of cost-benefit analysis was done to convince the client that this was a valuable expenditure for the site, and which benefits were observed in terms of, I don't know, improvements on different aspects of the design, nuclear regulation, and so on. Could you elaborate on that?
In actual fact, with this client, they didn't need much convincing of the value of installing this seismic array. So there was never really a need to present a cost benefit for it. I think they were aware of the IAEA guidance, and they took that on board.
But if you were
a very
to convince
enlightened
someone,
client.
yeah, but if you were to convince someone, which are the benefits for the cost? The cost first, I don't know if you have top of your head an idea of how much it cost, because it's not only the instruments I reckon, it's also all the characterization of the boreholes so that you can make the most of the data that you're obtaining. So what would be the estimated cost, and how do you see the benefits of that data in terms of potential savings for the design?
Yeah, I think the site investigation in any case would have needed the same level of data coverage. So I don't think there's much of an additional requirement in terms of ground investigation, because that's needed anyway for the site response analysis and site characterization for the foundation design. It's more about making sure that your boreholes, the borehole you select for your installation has been well characterized, is one of your better characterized boreholes. In terms of making the case for the installation, I can't remember the price off the top of my head, but the argument for installing it is really on the basis of it reducing uncertainties, and the knock-on effect in terms of the seismic hazard is that you're going to get, ultimately you can justify a reduction in your uncertainties around these input parameters, which allows you to have a more accurate estimation of the seismic hazard.
Thank you. We have one more question from Barali. Iain, very interesting presentation. Did the site-specific data lead to any changes in the kappa used in the PSHA?
Yes, it did. In fact, Guillermo, I think you could probably help us. Are you allowed to ask the the chairman
to answer questions?
That's right.
Probably. Well, it was quite useful. Unfortunately, because of the very small magnitudes that were recorded into that period, it was quite on the distance as well. We didn't have any records closer than 100 kilometers. So the data, let's say, for kappa purposes is not ideal, but still it was useful to inform the model that we selected, the best estimate and upper lower bounds. I think it helped to constrain particularly the lower bound, not to go too low on our original estimate. But the main challenge was that because of the small magnitudes, the corner frequency of the records was interfering with the range of frequencies that are required to calculate kappa. So, and also Angeliki, Olga Catanidou and one of her colleagues at the National Observatory of Hawthorn developed these noise cancelling methods where they are able to remove the noise from the ground motion record, particularly at higher frequencies and when they are really weak motions. That helps to improve the estimation of kappa. But even in that case, the number of records were limited. The use or useful records for Kappa purposes were limited, and the quality of the data was not great. So it was informative in an overall sense, but it was, I wouldn't say that it was conclusive. I think we had to wait for a bit longer, to particularly to record events closer to the station that then become more useful to characterize Kappa better. We have another question from Iain Smith. Brilliant presentation. Thank you all. The HVSR variation across the frequency range is fascinating. Any comments on what we might take away from this information, especially with the arbitrary codified approaches currently used? I think that is for Iain. Sorry, Angeliki.
Oh, please. I mean, I was going to say that, you know, being a site response person, that the HVSR, you know, the variation of the higher frequency maybe sort of denote that metrics like the VS30 are not necessarily sufficient, and we have we're not dealing with a unified block of ground, and these, you know, perpetuations sort of map the fact that you have you know, different geological units with different features. If that's, you know, where you're going with the question, I'm not quite sure if I answer this, but Iain, please feel free to comment as well. You know, aside from the predominant frequency,
we had what was really quite satisfying was the HVSR from single station surface measurements from microtremor gave us a very, very similar identical peak at the low frequencies as the HVSR from weak motion. And, you know, the weak motion is the result of, you know, it's likely to be mainly S-wave, vertically propagating S-waves, whereas for the HVSR from microtremor is a combination of waves, probably predominantly surface waves. And so this is a nice result because it's sort of giving us confirmation of a sort of 1D site from a 1D site response perspective, and also that you know, when we're doing our site response analysis, we're not modeling explicitly the rally waves and the love waves, the surface waves. We're assuming that we've got a simplified approach of vertically propagating shear waves. And so that it's nice to get a sort of weak motion confirmation of that rather than just a single station ambient HVSR confirmation. It was a nice sort of collaboration of this 1D approach that we took.
Okay, one more question from anonymous user. Given the IAEA guidance and OLR recommendations, does gaining site-specific data represents relevant good practice for PSHA?
Very much so, very much so. And you know, I think the ONR guidance and the IAEA guidance, which is about to be updated this year, and to reinforce the message, is that the benefits are significant. You know, it's really important to where we can reduce uncertainties in our inputs into the models, especially in a place like the UK with low seismicity. You know, we should take that opportunity to do that.
One more from me. Given the low seismic activity in the UK, how long do you have to have this type of instruments installed before you have any usable data? I think in terms of monitoring, it's pretty clear that the benefit is immediate, because as soon as you record an earthquake, then VGS is able to incorporate that into the network. But for engineering applications like site response or PSHA, how long do you have to wait before you have any valuable data?
mean, if I can just comment briefly and open it up to the others. So I think the constraint is more on the kappa. I think it's harder to derive kappa from weak motion data with high noise relative or low signal to noise ratios. Although Dr. Teniru and her colleague have demonstrated that this can be done even with very weak records. But from a site response perspective, you can, as long as you can identify an event, you can get pretty good estimate of the transfer function or the site effects between two of your instruments. Angeliki, you found this as well.
Yeah, absolutely. But I mean, let's not isolate these on low seismicity regions, because there's clear benefits as well for higher seismicity regions for validating the surface response with stronger motions. But for the site response analysis and the calibration of the velocity model itself, it worked immediately. So as long as we had a credible record, then we could do the calibration. And as Iain said, that had a greater impact on the kappa. But yeah.
Okay, I think then we are going to close out the presentation. Just a quick reminder about the next second evening presentation that will be held on the 29th of April at ICE. The topic of the presentation will be the second generation of Eurocode 8, key changes and implications, which will be delivered by Professor Ahmed Ghazuli and Sigil Lukovsky. The event will be an in-person event at the ICE, as I already mentioned. But you will have also the option to join online. Registration is not required unless that you are planning to join online. In that case, you need to register at the ICE webpage, so they will send you a link to join the event. Thank you to all the presenters. An amazing presentation. I think it was quite informative and instructive. And thank you to all the attendees. So I'm closing the event. Thank you. Bye.